At 3:14 p.m., the radar exploded with noise. False targets swarmed the screen, and no one could tell what was real. On September 4th, 2 Ukrainian F-16s cleared the cloud layer at 5,000 feet and closed on their target in a classic hook profile. The leader rolled inverted and pulled hard as the old analog airspeed needle climbed past 550 knots. The wingman peeled off and dove low toward the sea to split the defender's attention. The formation intent was simple: 2 angles. Force the defenses to choose, shrink reaction windows. The jets carried external tanks and a light weapons fit, short-range heat seekers, and a limited air-to-surface store. It was a hardware suited more to fighter work than modern anti-radar strikes. Systems and fittings showed age in service life and patchwork repairs. The kit read as practical but not modernized. The defended sight shifted to alert. Long-range sensors fed fused tracks into the Combat Information Center. Fixed arrays and point sensors combined into a clear, high-refresh picture. Shipboard or shore-based mounts spun up, and their barrels reached pre-fire speed. Fire control technicians watched track solutions form and confirmed intercept geometry. The radar produced updates many times per second, each pulse offering data enough to model motion and predict where to place effectors. The collective system did not wait on guesswork. It computed and presented firing solutions with matched timing. The leader broke his pop at about 500 feet and selected the only heat-seeking missile on his pylon. The seeker began its scan in the 3 to 5 micron band, looking for hot exhaust. There was no lock. The missile logic had been tuned for engine plumes near 1,000 degrees Celsius. The defended complex's exhausts and stacks radiated at a longer wavelength and far lower temperature. The weapon's spectral band did not match the target's thermal signature. Even if the seeker could have acquired a target, its range and off-bore sight limits made it an impractical anti-surface tool. The pilot had to point the aircraft at the object to hope for a solution, a constraint that modern off-axis seekers largely remove. The wingman leveled at roughly 50 feet, canopy wet with spray. His radio altimeter transmitted intermittent warnings below 500 feet. The unit had a known fault and had failed to be fully repaired due to parts shortages. He climbed from about 100 feet when the altimeter became unreliable and immediately collected radar paint from several arrays. His warning receiver indicated threats ahead only. The rear quadrants were blind or intermittent because of corroded antenna connections. He operated with partial situational awareness, vulnerable to sensors that would otherwise have been shielded by redundancy. The strike package lacked modern targeting pods and did not have GPS-linked guided bombs integrated into the mission computer. Interfaces for long-range anti-surface missiles were absent. The pilots attempted a low-pop launch and escape profile with weapons that were designed for air combat decades earlier. That mismatch of equipment to objective meant the attack depended on speed, angle, and surprise rather than standoff lethality. The defenders, however, were not configured like older opponents. Their sensor suite and missile systems accepted modern seekers and active guidance that reduced historical blind spots. The lead switched his mechanically scanned radar to tracking and lost the broad air picture. At 200 feet, the old processor could not filter sea clutter effectively. Waves produced returns that the radar interpreted as potential contacts. The ship's signature appeared and disappeared on the scope. The pilot adjusted gains manually while flying at low level and high speed, trying to find a stable return for targeting. The complexity of sea surface returns overwhelmed the legacy processing. Fuel bled fast under the afterburner. A few minutes of high-thrust flight consumed thousands of pounds of fuel. With no Link 16 or similar data link, the pilots resorted to hand signals to communicate fuel states and intentions. The lack of a common digital picture reduced their ability to coordinate precisely and forced them back to basic formation cues. They split again, one to the bow, one to the stern, the textbook method to divide defense effort. The defenders, though, could assign tracks to multiple weapon systems and handle many simultaneous inputs. The tactic that once forced prioritization now met a system designed to parcel and prosecute dozens of threats in parallel. Electronic measures entered the fight. Fixed-frequency radars, the sort that had been reliable for years, were susceptible to injected false returns. The defenders' systems received spurious contacts that multiplied, split, and vanished. The attackers' cockpits displayed impossible scenarios, the target appearing in the wrong place, then in several places, moving at speeds outside physical possibility. The defenders' workload increased. Operators had to sort real tracks from injected noise. The induced confusion bought moments, but did not eliminate the defenders' ability to match tracks to effectors. The lead pressed an attack through the electronic fog, diving from 3,000 feet and pushing past 550 knots. The airframe shuddered with wear rather than airflow. Years of deferred maintenance had introduced metal fatigue and weakened systems. Something behind the cockpit fractured and hydraulic pressure fluctuated. The flight control system, an analog set of compensations, lagged and smoothed inputs instead of reacting cleanly. Modern fighters use digital, redundant flight-by-wire. These aircraft relied on older circuits and patched redundancy. Shipboard fire control produced a perfect solution. A calculated time to intercept, measured in fractions of a second, and a precise volume of rounds to place on the track. The officer in control noted the power available in directed electromagnetic fields and the effect that sustained energy output would have on incoming electronics. Even without firing, the concentration of sensors and directed emissions changed the attacker's electronic state and produced instrument anomalies. The defenders had tools to overload legacy avionics and high-power radars to focus on specific tracks. The fighters made a final low pass at roughly 300 feet and then egressed. The mission did not score material hits. The effect was noise and expenditure of fuel. The defenders recorded every emission, every frequency, and every pattern. Intelligence teams stored those signatures for later analysis. The pilots returned to base, one managing a dead-stick arrival after engine trouble. Both aircraft required immediate checks. The sortie burned significant fuel and produced limited tactical effect, but it supplied a catalog of emissions and behavior for the defenders to analyze. At 2:47 p.m., the wingman climbed to about 5,000 feet to set up a slashing stern run timed at that minute. He carried known avionic degradations, radar altimeter faults, intermittent navigation drift, and a warning receiver with quadrant losses. He rolled and dove to engage from the stern vector. The defenders elevated their mounts, and the barrels spun to speed. Fire control radars acquired the inbound track and produced a lock with high fidelity. Sensor fusion combined radar kinematics, thermal overlays, and optical cues into a single tracked solution. As he committed to the run, the wingman's cockpit alarms began to sound. The defensive complex had shifted from broad surveillance to focused engagement and was concentrating energy on his track. His radar warning receiver screamed without the ability to classify modern emitters. Software and databases were outdated and could not parse the signatures. Instruments tumbled, artificial horizon errors, compass anomalies, and fuel indications that fluctuated. The cascade of failures was consistent with electromagnetic stress on legacy avionics that lacked recent updates. The pilot experienced a transient loss of coherent sensory input at high G load. The G meter pegged, and the pilot blacked out for a moment, recovering later at a higher altitude with disorientation and a metallic taste. The flight control system struggled to keep the plane within safe margins as hydraulic pressure dipped. Structural noises indicated overstress in the wing roots. The pilot considered ejection, but weighed the risk of seat-and-chute serviceability before deciding to remain. He recovered control and peeled off at about 800 feet, rejoining the leader. The defender's mount remained ready, and the firing solution lingered. One twitch of authorization could have produced catastrophic results. The wingman's run produced no physical damage. It did, however, yield intelligence. Precise RCS readings, emitter response timings, and instrument failure modes under directed energy. Engineers and analysts logged those artifacts and later correlated them with theater intercepts to refine emitter libraries and electronic warfare profiles. Operationally, the sortie showed the attackers' maintenance shortfalls and how those gaps translated into tactical vulnerability. At 3:14 p.m., the lead committed to a final attack run, applying maximum afterburner despite prior engine warnings. The earlier signs in the power plant, surge tendency, and micro-failures became decisive. Compressor stall recurred under stress, and the engine sustained damage until it quit. Asymmetric thrust pulled the aircraft off heading. The pilot reduced throttle to regain control and traded speed for handling. The aircraft entered a limited energy state with reduced maneuverability and little endurance. Defenders' thermal overlays reported engine temperatures well above safe limits. That heat signature became a targeting datum. The tactical officer computed an immediate firing solution with precision. Time to intercept measured in seconds and a calculated volume of rounds. The system was poised for engagement. The operator's finger hovered above the authorization switch. The pilots, in wounded aircraft, chose formation and withdrawal rather than pressing to a terminal engagement. They preserved their lives in aircraft where possible and returned toward friendly airspace. The lead executed an engine-out landing once the formation reached home airspace. Maintenance later confirmed the engine had exceeded overhaul hours and displayed compressor blade fatigue consistent with surge and thermal stress. The sortie expended large fuel reserves and yielded little damage to the defended complex. Intelligence harvest remained the main operational gain. Frequency logs, radar responses, and weapon selection records provided material for subsequent doctrinal adjustments. Post-sortie technical notes emphasized immediate needs. Frequency agile communications to resist interception and jamming, updated RWR databases to classify modern emitters, targeting pod integration for precise standoff effects, and prioritization of spare parts for altimeters and inertial units that produced navigational drift. The tactical lesson was plain. Legacy platforms could not close the capability gap by bravery alone. They required hardware and software parity to operate safely against modern, integrated defenses. At 3:30 p.m., the same crews prepared for a repeat sortie with orders to force a reaction and create exploitable signatures. Pre-flight checks showed inertial systems with drift and mission computers running old code. Radios used fixed encryption VHF without frequency hopping capability. The wingman's warning receiver still reported quadrant blackouts and horizon freezes for several seconds at a time. Command intent emphasized producing visible tracks to draw resources while probing with low signature elements to find seams. The formation executed the high-low split again. The lead climbed to altitude for a pop attack. The wingman hugged the surface in a sea-skimming approach. During the climb, the lead experienced another compressor surge. A loud bang, a temporary loss of compression, and a partial recovery. The pilots reduced the angle of attack and managed the engine back into a marginal state. The power plant data indicated cumulative hours well past recommended overhaul intervals and microcracking consistent with fatigue. Wide-area surveillance and allied assets had recorded takeoff and tracked climb. By the time the fighters approached the target area, several theater sensors had cued assets and relayed a shared contact picture. The defenders' situational awareness reduced surprise and increased the probability that injected decoys would be treated as the primary hazard. The attackers were therefore exposed to both direct engagement and analytic capture of their emissions. The lead rolled into a steep dive and used a fixed HUD reticle for final aim. Without a targeting pod or laser designation, release calculations relied on pilot estimation and legacy computing tables. The wingman's radar presented clutter. Waves and small returns filled the scope, and the system had no sea surface search mode to discard wave noise. The defenders continued to inject phantom contacts and to apply directed emissions designed to jam or saturate legacy receivers. Under EW stress, the attackers' avionic degradations reappeared. Instrument tumble, compass anomalies, autopilot disengagements, and fuel gauge oscillations. Their limited onboard ECM could not counter focused high-power measures. The pilots elected to withdraw when platform health and navigation reliability degraded below acceptable limits. Both jets returned and required immediate maintenance inspection. One performed a dead-stick landing as engines proved unreliable. Debriefing was concise and technical. Pilots and engineers presented logs, emission captures, RWR timelines, weapons selector positions, engine telemetries, and altimeter inconsistencies. Analysts cataloged the sequence into TTP nodes: deception to force attention, low observable probes to exploit seams, and rapid egress to preserve crews. The operational verdict was that the defenders' integrated sensors and active seekers had neutralized classic low-pop tactics without firing a shot in several windows, simply by creating a sensor environment the attackers' systems could not pass. Maintenance summaries listed critical faults: inertial units requiring recalibration, radar altimeter modules failing intermittently, RWR databases lacking contemporary signatures, and engines that exceeded recommended hours between overhauls. The logistics queue prioritized spares for altimeters, inertial reference units, RWR electronics, and overhaul parts for the F-100 series engines. Tactical change requests sought targeting pods, standoff anti-radiation or anti-ship weapons, and data link integration to allow shared situational awareness with partner assets. Intelligence outputs emphasized the value of the sortie as a signature harvest. The defenders now held a catalog of how legacy F-16s behaved under directed energy, what emissions they produced while attempting to jam resistance, and where maintenance gaps translated into tactical failure. Those records informed defensive update cycles and operator training. For the attackers, the records highlighted capability shortfalls and forced procurement and maintenance priorities. The operational analysis was reduced to practical prescriptions. First, fit modern data links so formations could share a common picture and avoid the finger count communications that reduced tactical cohesion. Second, upgrade radars or integrate targeting pods to give pilots precise, sea-surface-aware targeting cues. Third, prioritize spare parts to prevent altimeter and inertial drift that damaged navigation and approach safety. Fourth, update RWR software and emitter libraries to identify and react to modern directed emitters. Fifth, acquire or adapt standoff weapons that do not require closing to ineffective ranges. Field crews worked into the night. Technicians replaced corroded connections, patched wiring insulation, and scheduled engine inspections. Engineers began sourcing replacement modules for faulty altimeters and inertial sensors. Maintenance recorded the event as a stress test that exposed multiple chains of failure, aging hardware, missing spares, and incompatible mission interfaces. The operational ledger noted cost. Sorties consumed fuel and risk without material damage. The strategic ledger noted consequence. Defenders gained a detailed signal picture, and attackers faced a procurement backlog. The human reports remained spare and procedural. Pilots described instrument behavior concisely. Horizon freezes, fleeting loss of attitude, and intermittent navigational drift. Ground crews recorded the physical: scorched wiring insulation, weak solder joints, and cannibalized voltage regulators. Engineers added that some circuit boards were held in place by non-standard repairs and that several control racks showed thermal cycling consistent with overtaxed generators. Those facts shaped immediate maintenance triage and longer-term procurement lists. Analysts drew schematic timelines from the engagement. They noted the sequence: approach under cloud, low and pop profiles, injection of false contacts, defenders allocating to bright targets, low probes exploiting seams, and rapid egress. The pattern was familiar: distraction, absorption, breach, and harvest. Where older defenses had blind sectors, modern integrated sensors and active missiles closed those gaps. Where attackers relied on deception, defenders now had the tools to convert deception into intelligence yield. Doctrine notes reflected hard choices. Where previously speed and surprise could substitute for lack of range, modernity required either hardware parity or a doctrinal change toward standoff interdiction and integrated electronic warfare support. The recommended path combined procurement and tactics, bipods and standoffs, harden avionics with modern RWR and data links, and practice integrated missions with allied electronic warfare cover that could create reliable windows rather than reactive confusion. If you found this breakdown as gripping as we did, make sure to subscribe and turn on notifications as more real combat stories told exactly as they happened are on the way.